Okay, good evening, everybody. And welcome to another session of organic chemistry. For today's session, we are going to start our discussion on Chapter 17. Of course, Chapter 17 is concerned with the chemistry of alcohols and phenols. Okay, before we do that, just a couple of announcements. Your exam has been graded, and I will give them back to you at the end of the session today. And also, our homework assignment for this week has been posted in Blackboard. And the due date is Sunday, February 17 at 11 p.m. If there is going to be any change due to the expected snow that we are expecting on Thursday, I will email you to let you know if there will be a change in the due date. Okay, okay, so let us get today's session started. Okay, we are discussing Chapter 17, which is the chemistry of alcohols and phenols. The good thing about this chapter is that most of what we are going to discuss, most of them we have already done in previous chapters. So hopefully this will be like a review to most of you. Okay. We'll be discussing synthesis of alcohols. Most of them we've done in previous chapters, and also reactions of alcohols. Most likely what is going to be new will be the synthetic strategy, putting all the pieces together. Of course, on this slide, you have a list of learning outcome objectives. For example, at the end of this chapter, you should be able to write the IUPAC name for alcohols. You should be able to write structures for alcohols when giving the IUPAC names. In other words, take a look at all of the lists that you have on this slide, all of the concepts on this slide, and use this as a study guide. So at this point, we want to ask, what are alcohols? Now, alcohols are those organic compounds in which you have the hydroxy group, which is this here, attached to an sp3 carbon atom. So alcohols are organic molecules in which you have the hydroxy group attached to sp3 carbon atoms. And because of that, we have three different types of alcohols. We have what we call the primary alcohol, in which the hydroxy group is attached to a primary carbon. Of course, you know, a primary carbon is that in which you have in which the carbon is only attached to one other carbon atom. Okay. And then we have the secondary alcohol. In this case, the hydroxy group is attached to a secondary carbon, right here. And finally, we have the tertiary alcohol, in which the hydroxy group is attached to a tertiary carbon, this right here. Okay, so let me give you some more specific examples of this. The simplest alcohol is methanol, and then the simplest primary alcohol is ethanol. See this here. As you can see, in the case of ethanol, this is methanol. In the case of ethanol, the hydroxy group is attached to a primary carbon. Of course, methyl alcohol, methanol is a special case by itself because the hydroxy group is only attached, it only contains one carbon atom in that molecule. Then we have this. Because 2-propanol you see here, this is a secondary alcohol. The hydroxy is attached to a secondary carbon. And then we have this. Okay, this becomes 2-methyl to propanol. I'll give myself some space here. Two methyl, 2-propanol. So in this case, you can see here the hydroxy group is attached to a tertiary carbon atom. In this chapter, we are also going to discuss very briefly phenols, which of course we did in the last chapter. Now, phenols are those organic molecules in which you have the hydroxy group is attached to the benzene structure. Okay, so we call this a phenol. We also call this a phenol. Phenol is a class of compounds in which you have the hydroxy group is attached to the benzene fragment. Okay, this will also be called a phenol. As you can tell from the previous chapter, this here is also a phenol. As long as you have the hydroxy group attached to the benzene molecule, then we say that is a phenol. Another class of compound that is related to alcohols are what we call enols. So you want me to go back? Okay. 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 Yeah, another class of compound related to alcohols are enols. In the case of enols are those molecules in which you have the hydroxy group is attached to a carbon-carbon double bond. So this would be an enol. Okay, we are going to discuss more about enol, I believe, in chapter 19. Okay, but these are molecules in which you have the hydroxy group attached to a carbon-carbon double bond. Now, these type of molecules are not very stable because they do rearrange very easily. The enols rearrange very easily to the corresponding ketones or aldehyde. So in this case, this is the keto form of the enol. So we are going to discuss this when we get to chapter 19. Okay, but before I go further into the discussion on alcohols, let us briefly discuss the physical properties of alcohols. If you take methanol, this molecule here, the boiling point of methanol is 65 degrees Celsius. Then you go to ethanol. The boiling point is 78 degrees. Then we go to our propanol. Boiling point is 97. Then we go to butanol. Boiling point is 117. Now, does anybody detect a pattern here? Now, what is that pattern? Okay, as you increase the molecular weight, right? The boiling point increases, right? That is correct to some extent. That is correct. Supposing, before I come back to that, supposing I give you this. We all know that as water. Indeed, if you take a look at water molecule and the alcohols, you could almost think that the alcohols are indeed derivatives of water. Because what we have here, all we've done in the alcohol is to replace one of these hydrogens here with a carbon-containing group right here, in the case of methanol, or in the case of ethanol. So in other words, we are replacing one of the hydrogen in water with an alkyl group for us to get an alcohol. So we can't consider that the alcohols are derivatives of water. Now, but if you take a look at the boiling point of water, it's 100 degrees. And the molecular weight of this is what? It's probably this very small molecule. Molecular weight of water is only about 18 atomic mass unit. So if we are only concerned with the molecular weight with relation to the boiling point or some of the physical properties, then how do we explain that water has a higher boiling point than methanol, than ethanol, than propanol? How do we explain that? Hydrogen, very good, very good. Hydrogen bonding, you guys already know exactly where I want to go here. Hydrogen bonding, because the difference here, you have a lot more hydrogen bonding in water. I'm sure, does everybody know about hydrogen bonding here? So I don't have to do this. Okay, so I will just close this right here, right? Okay, anyway, so very briefly, let me say here, intermolecular you find that all molecules, somehow they have to be held together by some forces. These are what we call non-covalent bonding. In the case of water, you have what we call hydrogen bonding. So let me list these intermolecular attractive forces. One is hydrogen bonding, just as you guys have correctly said. Two is dipole-dipole interaction. Three, what we call van der Waals forces. Of all these three interactions here, in terms of the strength, the hydrogen bonding here, this is the strongest. And this is the weakest. The van der Waals forces are the weakest. So in the case of water, what do we have? We have extensive hydrogen bonding, because hydrogen is bonded to oxygen. So you have another molecule of water, be here. So you have what we call very weak, this is not a covalent bond, very weak bonding between this hydrogen, because the hydrogen is slightly, the bond between hydrogen and oxygen is polarized. So this hydrogen has a slight positive charge to it, and of course the oxygen has a slight negative charge. Same thing here, same thing here. So you have this chain of hydrogen bonding from one water molecule to another. Okay. Sorry about that. I mean, better than that. So you have this here. So the point is, for any water molecule, you see a chain of hydrogen bonding. And in order for you to break those hydrogen bonding, you need to apply some heat. So the more hydrogen bonding you have, the more heat that you need to generate in order for you to break the bond between all of the different molecules. I don't know how many of you have dived into a swimming pool, face straight into the water without going in with your hand before. How many of you have done that before? You notice it's very painful, right? What you are doing is breaking those hydrogen bonding. Because those hydrogen, they form a layer, very strong layer, and you dive into it, you find that if you've done it before, it's really very painful. It's very, very difficult to break. So anyway, that is why water has a boiling point of 100 degrees, as opposed to, in the case of methanol, okay, you only have one oxygen-hydrogen bond here. So the hydrogen bonding in methanol is not as extensive as in the case of water. So that is why water will have a higher boiling point than methanol. And then, of course, as you guys rightly suggested, as you increase the molecular weight of all of these alcohols, you also have an increase in boiling point. And that is due to what we call the van der Waals interaction, this here. For example, imagine that you have a molecule this big, and then you have the methanol or ethanol, which is this here, this big, a little bigger. Molecules are essentially, you could think of them as almost as an envelope of electrons. You have electrons surrounding them. All of these electrons are moving around, and as they move around within the molecule, they form what we call temporary dipoles. So it is possible, the bigger the molecule is, the greater the chance of forming the temporary dipole. So it is possible this part of the molecule may have partial negative charge, and this part may have partial positive charge. Okay, and then you have another molecule here, the same thing happens, partial negative charge, partial positive charge. And therefore there is this dipole-dipole interaction between them, holding them together. But those forces are not as strong as the hydrogen bonding. The bigger the molecule, the bigger the van der Waals interaction. And that is why as you increase the molecular weight of a molecule, you do increase the boiling point of that molecule. So therefore, supposing I give you this. I give you a list of molecules and I say, give me the order. What you consider would be the order of boiling point. Supposing I give you this here. Then I give you this here. Let us call this A, B, and C. And I say arrange this molecule in the order of boiling point, from low to high. Which will be the lowest and which will be the highest? Which will be the lowest? A, okay, very good. And then B, and then C. Why? Why? Okay, because C will have a greater hydrogen bonding exactly, okay, than A. Okay, and the same thing happens to any molecule in which you have hydrogen is attached to an heteroatom. Heteroatom simply means these are non-carbon or non-hydrogen atoms. For example, nitrogen, oxygen, sulfur. Anytime you have hydrogen attached to any one of those atoms, there is a possibility of hydrogen bonding. And as such, you expect that the boiling point will be higher than the comparable molecule that do not have similar hydrogen bonding. Okay? Okay, so that's all we are going to say about the intermolecular attractive forces. Now let us now get to the nomenclature of alcohols. Okay, the nomenclature of alcohol, the IUPAC nomenclature, is derived from the name of the corresponding alkane or corresponding alkene. As we've given you already, we told you earlier, this is methanol. Okay, the corresponding alkane will be methane. So what do? We remove the E ending of methane or the corresponding alkane and we replace with OL. Okay, OL is what we call the suffix, in other words, the ending. for alcohols. Anytime you see OL at the end of an IUPAC name, you know you are dealing with an alcohol. Huh? This is ethanol, even though the common name is ethyl alcohol. Ethanol. Okay, remove the E ending of ethane, replaces OL, you get ethanol. Propanol. Now let us look at more complex molecules. Supposing I have this. What are we going to call this? Keep in mind, the focus is on the hydroxy group. Okay, the hydroxy group is the focus. Okay, what you do, you look at the carbon to which the hydroxy group is attached, and you assign the lowest possible number to that carbon. Okay, in the first place, you're going to have to look at the longest carbon chain that contain that hydroxy group. Okay, so if you take a look at this molecule here, how many carbons do you have in the longest carbon chain that contains the hydroxy group? 8? Okay, very good. Then where do we want to start numbering? From here or from here? From the left? I say left? Or right? From right. Okay, why? Because the hydroxy, very good. You want to give the hydroxy group the lowest possible number. So this becomes 1, 2, 3, 4, 5, 6, 7, and 8. So therefore, that means we now have a substituent on carbon number 7 and another substituent on carbon number 5. Okay, so what will be the complete name for this molecule here? 5-ethyl. Okay, keep in mind we still have to follow the alphabetizing order. Okay, very good. 5-ethyl, 7-methyl. Okay, now 3. Okay, 3. Okay, octanol, very good. 3-octanol. You could also use the more recent nomenclature, IUPAC nomenclature, in which you simply, okay, this name here, this is correct, but this is the older nomenclature, it is still acceptable, in which you indicate the position of the hydroxy group before you give the name of the parent molecule. However, you could also do this. 5-ethyl, 7-methyl, methyl, octa, okay, octane. Before you then use the suffix, you now have hyphen 3-O. Okay, so you now use that to indicate the position of the. So any one of these that you are comfortable with is fine with me. Okay. Now supposing we have this. If you have an hydroxy group attached to the ring, in this case, you do not have to indicate the position of the hydroxy group. Okay, so this becomes cyclohexanol. Supposing we have this. What are we going to call this? Keep in mind the hydroxy must be given position number 1. So this is 1, right? Very good. 1, 2, 3, 4, 5, and 6. So this becomes 3-bromo cyclohexanol. Notice you do not have to indicate the position of the hydroxy group if you only have one hydroxy group in that molecule. Now supposing you have more than one hydroxy group. Supposing I have this. Supposing I have this. Okay? Here, now you have to, of course, you have to assign numbers to the substituent. So this is 1, 2, 3, 4, 5, 6. Of course, you assign numbers to those hydroxy groups so as to give them the lowest combination of numbers. So now in this case, we now have the bromine in position number 5. So what are we going to call this? 5-bromo, 1,3, very good, 1,3 cyclohexane, exactly, cyclohexane. This time, you do not remove the E ending, because it would be very awkward to have, anyway, become cyclohexane diol. You know, it would be awkward to have cyclohexane, and you want to remove the E ending and say D, that would be very awkward, right? So that is why we think we leave the E whenever you have more than one hydroxy group in the molecule, okay? Okay, so this becomes 5-bromo 1,3 cyclohexane diol. Now, supposing you have this. What are we going to call this? And where do we start numbering? This is my left, and this is my right. Start numbering from the left, very good. So we have, therefore, say this is 1, 2, 3, 4, 5, 6, and 7. Okay, so what would be the name for this? Okay, that is 2, 3, right? 2, 3, 5, very good. 2, 3, 5, okay. Heptane, okay. Heptane. Keep in mind, keep the full name of the alkane. Where did that come from? Heptane triol. Okay. Okay. 2, 3, 5 heptane triol, or you could also use the more current name. Simply say heptane. So, heptane. Okay. Then 2, 3, 5 triol. You also do that. Okay? So anyway, I'm going to leave the rest of our nomenclature for you guys. Most of you who are looking at your book, there is a lot of problems in the back of your book that you should be working on Okay, at this point, let us go to the synthesis of alcohol. This is where you're going to find that most of this we've done before. So what we are going to do now will be sort of like a review to give some of you a chance to recall all of those reactions that we've done previously. Synthesis of alcohol. Okay, but before you start writing that, let me show you this. You see on this chart, this chart simply demonstrates to you the centrality of alcohol in organic chemistry. If you go from an alcohol to all of these classes of compounds, and vice versa, if you go from any one of these classes of compounds to an alcohol, you see here the alcohol is sitting right in the middle of organic chemistry. Okay, so by the time we finish this chapter, we should be able to go from here to alkyl halide, to ester, carboxylic acid, alkene, ketone, aldehyde, ether. So all of this we should be able to do, and vice versa. Go from, for example, go from a ketone to an alcohol. Okay, so let us go back. Synthesis of alcohol. So we are going to start with, I'll say from alkene. Okay. Okay. I will number this to make it easy for you. First one is the chloration, oxidation. As you know, if you take an alkene and we take borane, followed by hydrogen peroxide in basic medium. Okay, what do you expect to get? Let me number this. This is 1, 2, 3, 4, 5, and 6. Okay, where do you expect where we are going to add water across this carbon-carbon double bond? That is what this reagent will do. Okay, so where do you expect the hydrogen to go, and where do you expect the hydroxy group to go? Hydrogen goes to 1. Okay, very good. Okay, the hydrogen goes to carbon number 1. Just so happens that this reaction is stereospecific. Okay? In other words, we are going to add two water molecule across the carbon-carbon double bond, so that the hydrogen and the hydroxy group will be added from the same side of the double bond. Okay, so we say this is stereospecific. We've done a lot of this reaction before, so we don't need to spend too much time on this. Of course, that means that this here is coming at you, and then you have an hydrogen here coming at you. We could also use, let's say 2, the same molecule. We take mercuration. Make it easy for you. Let me take this out. Mercuration, demercuration. In this case, if you take the same molecule, as above. Oh, by the way, we say this is an anti-Markovnikov addition. Anti-Markovnikov addition of water across the carbon-carbon double bond. Now, if we want to obtain the Markovnikov addition of water, we use this reagent here. Mercury acetate. Generally, you use this in an aqueous medium. Step 1. And then you follow that up with sodium borohydride. You guys know about that already. And then we get a Markovnikov addition of water across the carbon-carbon double bond. In which case, the hydroxy group goes here, and the hydrogen goes here. Now, this is not a stereospecific reaction. Okay? Notice we do not show stereochemistry here. Okay, so this is Markovnikov addition. Of water. So the point to be made here, you need to know these reagents. If I give you this reagent here, and I give you an alkene, you say, oh, okay, all it does is to add water across the carbon-carbon double bond in an anti-Markovnikov fashion. You should be able to say that in your own words. When you say that, then you understand it. Okay? Don't just read it. You should be able to say it. Same thing with this reagent here. This reagent here. You take a look at this reagent, you say, oh, this reagent, mercury acetate, followed by sodium borohydride. What does it do? It will add water across the carbon-carbon double bond in a Markovnikov fashion. In other words, the hydrogen goes to the carbon that has more hydrogen, in this case, this here, and the hydroxy group go to the carbon that has less hydrogen. Okay? That is the Markovnikov addition. Everybody got that? Okay, so we also keep in mind we are still dealing with from alkene. Okay, we also could take, let's call this 3. I will say hydroxylation. Hydroxylation using osmium tetroxide followed by sodium hydrogen sulfide, followed by sodium hydrogen sulfide. Okay, all of this is still from alkenes. Okay, so if I take an alkene, by the way, hydroxylation means you are adding 2 hydroxy groups across the carbon-carbon double bond. If I take that, and I take osmium tetroxide, and then I follow that up with sodium hydrogen sulfide, what do I get? What does that reagent do? You have to be able to say it in your own words. What does it do? Add 2 OH groups across the carbon-carbon double. In what fashion? 6 addition fashion, exactly. By now you should be able to begin to compile a list of reagents. it's better for you to compile your own list, because when you do that, you tend to remember the list better than if somebody gives you their list, because then it becomes another book. You should be writing your own book. When you write your own book, you remember it. But if you simply just get somebody's list, it's just another book. You might as well just read your book, right? But make up your list. It's going to be a very big list, and you'll be very happy at the end that I really put together almost a book, but you remember it. You're not just putting it together, but you have to remember it. So in this case, this will add hydroxy group across the carbon-carbon double bond, two hydroxy group in a cis addition fashion. In other words, those two hydroxy groups will be on the same side of the molecule. They are added from the same side of the carbon-carbon double bond. So that means our metal is coming at us, and this hydrogen that was there before is coming at us. Don't forget there is hydrogen here. Okay, that's number 3. Number 4. Hydroxylation. Via epoxide formation, followed by epoxide opening, with dilute acid. Okay? For example, I do this. In this case, the addition of the two hydroxy groups, because this is hydroxylation, will be done in a trans addition fashion. Okay? So we take this. To form the epoxide, you use M-chloropar benzoic acid Okay, we generally refer to this as MCPBA. So if all you do is just write MCPBA, that is fine with me. M-chloropar-benzoic acid. When you do that, what that reagent does is to form an epoxide to add an oxygen across the carbon-carbon double bond. That's all it does, to add an oxygen across the carbon-carbon double bond. Okay? Of course, you could stop the reaction right here, but if you want to make your diol, then you take the epoxide, you add dilute acid to it, then you open up the ring. The two hydroxy group are now on opposite side of the molecule, and of course you still have the metal still here, and the hydrogen is still here. Okay. Ordinarily, yes. Say that again. Oh no. Yes, at this point I wouldn't. If the mechanism is important, I'll give it to you. Okay. Okay. Now, ordinarily, the way we do this If we simply just do this here, okay, step 1, M-chloroparbenzoic acid. Okay. Then step 2, if what we want is the diol. Okay. So you just say step 1 and step 2. Okay, so what I've done now so far, I've shown you how to make alcohols from alkenes. Now let us now take a look at how do we make alcohols from carbonyl compounds. Okay, so that was number 4 I gave you. Okay. Okay, now say from alcohols from carbonyl compounds. I'll call this number 5. Yes. Say what? Is there any reason? Okay. Okay, yeah. This one here. Why this reagent will add trans? Okay. Okay. Don't forget we told you if you just do the M-chloroparbenzoic acid, okay, you form the epoxide. Okay. Now, keep in mind now you have the epoxide on one side of the ring. So what is going to happen when the water comes in? In this case, the water will open up the keep in mind that this happens in dilute acid. First thing that happens, you have acid here. And keep in mind that anytime you have oxygen, you always have non-bonding pair of electrons. In other words, what you are asking me, you want to see the mechanism. Okay? So here, okay, so you protonate that oxygen, and once you do that, then water comes in, attack this here, this epoxide as a nucleophile. This is now your nucleophile. Water is your nucleophile. Because the ring is on, think of it that you have the cyclohexane ring, the epoxide is on this side. So the water has no choice but to come from behind. Okay? So what does it do? And when it comes from behind, it opens this up. When it opens that up, and that's where you get your trans addition. Because the other water actually is coming from the other hydroxy group is coming from the water. So now you have that open up, so that you have this here. And then the water comes from behind. Okay, the water comes from behind, of course. We also have this here. Okay, so now at this point, another water molecule comes here to relieve this oxygen here of this proton here. And then you release the 2 electrons to oxygen, and you get your final product. Okay? So anyway, that is basically the mechanism for that reaction. You form the epoxide first, and then water comes in as a nucleophile, open up the epoxide from the back, and that's why you get your trans product. But anyway, for the most part, unless if I don't give you the mechanism, nobody is going to be asking you for mechanism. Okay. Okay, so we say we want to go to 5. Now, this is from carbonyl compounds, right? Okay, 5. I start with the metal hydride reduction of metal hydride. You guys have seen this before. Reduction of aldehyde and ketones to give primary alcohols and secondary alcohols respectively. In other words, you get the primary alcohol from aldehyde and the secondary alcohol from ketones. Now, what do we mean by metal hydride? These are these here. Sodium borohydride, you guys have seen that before, sodium borohydride. And lithium aluminum hydride. Those are the two that we use. Okay? Now, if I take, let me take this aldehyde here, and I take sodium borohydride. I follow that up with water. I get this. Primary alcohol. Now, this is where the mechanism is very important. It's important because it is a mechanism that we are going to be using in so many different instances. Okay, so I'm going to give you the mechanism for this reaction. Whether you use lithium aluminum hydride or sodium borohydride, each one of these reagents, what they do is to supply what we call hydride, negatively charged hydrogen. Okay? So therefore, let us look at what happens here. So you have the hydride comes in as a nucleophile. So if I ask you for the mechanism, just start with the hydride, okay? Because that is what this reagent will do. That's what they do, supply the hydride. the hydride comes in, acts as a nucleophile, attack the carbonyl. Of course, the pi electron goes to oxygen, and then you get this. Let me change the color of this hydride here so we know. Let's make this green. Okay? Okay, so it is coming from here. And then, once we get this intermediate here, of course, you now add the dilute acid. Sometimes generally we use dilute acid because dilute acid. What the dilute acid does, these alkoxide here, this negatively charged oxygen comes in here to pull off this proton from the dilute acid. And then you get this. So actually, if you look at this, it's essentially you are adding two hydrogen atoms across the carbon-oxygen bond. That's what we're doing here. Because one of the hydrogen comes from the metal hydride, this here. The other hydrogen comes from the dilute acid or from the water. Okay? Let's just make that dilute acid. Okay? So, yes. I can hear you. Say that. The A3, where does it come from? Right here? Right here? Right here? Because at the end, don't forget, the first thing we do, after the sodium borohydride reaction, then we add the dilute acid. That's where this is coming from. Okay? Okay. Now the same thing happens with lithium aluminum hydride. Keep in mind, we say, in the case, we take sodium borohydride, followed by dilute acid. In this case, we form a secondary aqueous, because all we are doing is adding two hydrogen atoms across the carbon-oxygen bond. That's what we're adding this hydrogen and this hydrogen across the carbon-oxygen bond. One of them is coming from the sodium borohydride, the other is coming from the dilute acid. In this case, we are forming a secondary aqueous, yes. Yes, yeah. The metal hydride, all they do is supply the hydride. Okay, so if I ask you to give the mechanism, all you have to do is start from the hydride. Now the same thing will happen here. Step 1, lithium aluminum hydride, followed by dilute acid. Get it, sir? Hmm? Now if I have this, if I start with this aldehyde, okay, I will get sodium borohydride. Step 1 and step 2, dilute acid. I get a secondary aqueous. Okay, the same will happen if you do perform the same reaction with lithium aluminum hydride. As a matter of fact, lithium aluminum hydride sometimes we abbreviate as LAH, lithium aluminum hydride, and then follow that up with dilute acid. Yes. Because we are starting with a ketone. If you're starting with a ketone and you add hydrogen here, and the other hydrogen goes to oxygen, you get this here. But if you're starting with a secondary, I would say with an aldehyde, okay, this aldehyde here, you only add, keep in mind at this point, the aldehyde, you only have one carbon attached to this carbonyl, so therefore you are going to form a primary alcohol. Huh?
That's the bottom.
What do you mean bottom ring?
Bottom where you have the benzene.
Say that again?
Well, the bottom when you have like the benzene and the carbon.
But the reaction is taking place on this carbonyl. This is an aldehyde.
Yeah, because you said secondary.
Oh.
When you're doing the bottom, you said secondary, so I'm sure.
Okay. I say if you start with a ketone, you get a secondary alcohol.
Yeah.
But if you start with an aldehyde, you get a primary alcohol.
Yeah, I get that.
Okay.
But I was saying when you're doing that, you said secondary.
Oh, I said, oh, okay. Okay. Sorry about that. Okay, yeah. Okay, now, so we've done the metal hydride reduction. Now, that was 5, right? 6, still dealing with alcohol from carbonyl. Okay, this would be LAH reduction of carboxylic acid to give primary alcohol. In other words, if I take a carboxylic acid, this only happens with lithium aluminum hydride. Sodium borohydride does not do that. So that is why I made it specific for lithium aluminum hydride. If you take a carboxylic acid and you take lithium aluminum hydride followed by dilute acid, okay, so what you get here, this carbon here will be turned into a primary alcohol. Okay, notice this carbon here. This carbon now becomes this carbon. Now gets reduced to the primary alcohol. Now this only happens with lithium aluminum hydride, not sodium borohydride, yes. It is the same mechanism. The next reaction I will give you a similar mechanism that will apply to this. Okay. 7. LAH reduction of ester to form LAH stands for lithium aluminum hydride. LAH reduction of esters to give primary alcohol. Once again, this only applies to lithium aluminum hydride. Sodium borohydride does not do this. Supposing I have this. So I start with that ester, methyl ester. I have lithium aluminum hydride followed by dilute acid. Once again, we get a primary alcohol. So let me give you the mechanism for that reaction. This is similar to what I gave you before, but there's a slight difference here. That's why I want to give you this mechanism. Okay, so mechanism for LAH. Reduction of esters. To give primary alcohol. Okay, I will stop in a few minutes, so I will give you back your papers. Let's see. We do this, and that will be it for today. Now, say we start with this. Let me use that same specific example I just given you. So you start with your hydride. Okay? Negatively charged hydrogen. And what is going to happen? Hydride comes in, attacks the carbonyl. In all of these cases, the carbonyl carbon is the electrophilic site, and the hydride is your nucleophile. Let me change the color to green, make this green so that we could follow it better. Okay, so that hydride from the hydrogen from lithium aluminum hydride has attached itself to this carbon here. Okay, this is just an intermediate, and what is going to happen, this intermediate will regenerate the carbonyl, and in so doing, something has got to give on this carbon. Carbon cannot have more than 4 bonds, so the oxygen-carbon bond will break. Okay, to form this. Now, what have we done here? What is this intermediate that we formed? What class of compound is this? That's an aldehyde. And guess what? The aldehyde is very reactive towards lithium aluminum hydride. So what's going to happen now? Another hydride comes in, and so that is how you get your primary alcohol. Because the intermediate that you form is an aldehyde, in this case, in the case of reaction with an ester, the same thing happens with reaction with carboxylic acid. So now that comes in, attack this again, and this comes here. So now we form this intermediate. Now, use my green color here. These two hydrogen now came from lithium aluminum hydride. Okay? And now what happens at this point? What do you think will happen now? We are now going to add the dilute acid. You add the dilute acid, so what's going to happen? The alkoxide, which is a negatively charged oxygen here, will come in and simply just grab the proton from the dilute acid, and that is how we end up forming the primary. This hydrogen is from the dilute acid, and the other two hydrogens here, this here and this here, is from the lithium aluminum hydride, okay? From LAH. Okay. And that is how you go from an ester to a primary alcohol. Supposing I give you this problem, real quick. Supposing I say this. So give me the reagent for this, real quick. Give me the reagent for this.
The lithium.
No, okay, let's see. Okay, give me the reagent for this reaction.
The NADH.
Exactly. Okay, so that is why at this point you use the sodium borohydride. Why? Because if you use the lithium aluminum hydride, both of these functional groups will be gone, right? So that is how we use this in synthetic strategy. Okay, so at this point we have come to the end of today's session. I have a feeling that on Thursday we may not have a class. You guys want to continue for another 30 minutes? We may not have a class on Thursday, you know that. So that's my problem, right? Okay. Okay, anyway. Huh? So that? The only... Just a minute. So I guess I will see you guys I will see you guys on Thursday.